In this part of the course, we're going to move through some example sites for the sun, the stars, the moon, and the planets. We're going to move pretty quickly through all 5 steps of the process. So if you get stuck anywhere, be sure to go back and review that part of the course. But for now, let's get some practice. Our first problem is a sun site reduction, and as I mentioned earlier, we're going to move through this relatively quickly, so if you get stuck on any particular step, be sure you go back and look at that in the course material. Step number 1, take our HO and HS and convert it to an HO. So our height of sextant was 2300.7, and we need to then correct it for index error, dip, and apparent altitude. So in the problem, it mentions that our index error correction, or our index correction, is going to be plus 2.6, and we need to look up our dip correction because we've got a height of I of 55 feet. So for a height of I of 55 feet, we're going to have a correction of negative 7.2. That's going to get us to our height apparent. Height apparent is height of sextant corrected for index error, and dip, and that's 2256.1. From there, we can take our height apparent and we can go into the apparent altitude tables. We'll choose the correct month. So it's January, the lower limb, and it was the sun. So we're going to go down and try to find our height apparent, 2256.1. It's not in there, but our correction is going to be plus 14. So that gets us to our HO, our final answer for step 1 of 23 degrees, 10.1 minutes. So step 1 complete, HS to HO. We'll note this HO and we'll move on to step 2. For step 2, we need to find the position of the sun at the exact time of the site. First things first, this is in local time or zone time, so we need to convert it to Greenwich Mean Time. So if you take your DR longitude, 124.5 basically. Sorry, I have a finger issue. Didn't know I was a hand model. If you divide that by 15, since there's 15 degrees per time zones, that's going to give you how many time zones you are away from Greenwich. So you can round to the nearest number. We're 8 hours away from Greenwich. So that means our GMT is going to be 17:15:36. GMT. So that's the time that we'll look up for the sun's position. So then we're going to go and get the declination and the GHA out of here. So we'll go to 10 January. And we'll need to find the GHA and declination of the sun for the GMT time. So first we'll note the hours, and then we'll note the increments using the increments and corrections pages. So for the declination, the hourly declination is south 21 degrees, 53.6. All right, so here's the 21 degrees, 53.6. We also note that it's decreasing and that the D number is 0.4. So D number is 0.4 and it's kind of decreasing. So that's all good information to note now. While we're here, let's just look at the GHA as well. So that's 7304.5. 7304.5. So for GHA, that's 7304.5. So now we can go to the back of the book and get out the increments. So for this leftover time of 15 minutes and 36 seconds, we'll go to the increments and corrections pages for 15 minutes. All right, so 15 minutes and 36 seconds for the sun is equivalent of 354 for the GHA. So that's 354 more. We'll save that addition for a minute. For the declination, we just need to look at the D number. So the D number was 0.4, so the correction is 0.1. 0.1. And since it was decreasing, it's going to be minus. So now we can solve these in whatever order that you like. So for the declination, it ends up being south 21 degrees, 53.5. For the GHA, that ends up being 76 degrees, 58.5. So So we've got our declination and our GHA. Step 2, complete. We'll note that information and we'll move on to step 3. For step number 3, we need to get our entering arguments for HO225. So we need a latitude, a declination, and an LHA. So for the latitude, very easy, just choose the closest whole latitude. So our latitude is going to be 26 degrees north in this case. For the declination, also very easy, just choose the whole values of declination, not rounded. So 21 degrees south in this case, so we're going to be contrary. For the LHA, that's a little bit more work. We need to take the GHA minus the longitude since we're in the Western Hemisphere. So we can add 360 to the GHA. So if we add 360 to the GHA, that ends up being 436 degrees, 58.5. Then we subtract the longitude, 124 degrees, and we can round it so that it's within 30 minutes, but such that this math comes out to 0. So we're going to go 58.5 for our assumed longitude. And so when we do that, our LHA comes out to a whole number of 312. So we've got our values for HO229, our latitude 26, our declination 21 south, and then our LHA 312, noted contrary pages. So next, step number 4, we're going to go into HO229 and retrieve some data. Before we do, I just want to highlight that I've adjusted some of the data up here. So I changed our DR position to our AP, and I noted our LHA up here. So this is stuff that we're keeping for later. So we need to go into HO229 and find the page for LHA 312, latitude 26, which means it'll be the back of the book, and then look into the declination. All right, so here we've got an LHA of 312. We're contrary pages, a latitude of 26, and a declination of 21. So when we pull that stuff out, right here we can see our HO, our D, and our Z value. All right, so we'll note that it's negative for the D value, and we'll note all that other information down. So we noted that our HC value, computed height, was 2351.1. And I think I misspoke a second ago. I called it HO, but it's HC. Our D value, our altitude difference, is negative 41.1. And our Z value, our azimuth angle, is 130.7 degrees. So the next step is to kind of correct this stuff. So we're going to correct the HC for declination increment first. So if we take 41.1 times the increment for declination, all divided by 60, that gets us our correction. So we'll note that it's negative. So negative 41.1 times 53.5 divided by 60 is a correction of negative 36.6. So we can make that correction right now, and our HC comes out to be 23 degrees, 14.5. That's our corrected HC. Always a good idea right now to check that with the HO from earlier. You know, if they're pretty close, you're okay, within about 30 minutes. Otherwise, you might have made a math error, and it's worth going back to check before you go further. All right, now, sometimes it lives in step 4, sometimes it lives in step 5, but we can correct this azimuth angle if we want as well. So since we're in the mood, we'll just kind of do that. So our declination increment was 53.5. If we look into HO229 for the next subsequent Z value, we can see that there is a difference from declination to declination, and the next tabular Z is 131.5, so there's a Z diff, or Z difference of 0.8 plus. So, the declination increment times this, all divided by 60, will give us our correction of 0.7. So a 0.7 correction. So that ends up with a total Z of 131.4 degrees. Next, now remember this part right here you can definitely ignore because it's such a very small correction, but if you want to do it for completeness, go for it. We need to refer to our azimuth rules. So we're in the northern hemisphere, and our LHA in this case is greater than 180. So in this case, Zn equals Z. So our azimuth angle also equals our azimuth. So this equals Zn as well. So we've got our HC, we've got our Zn. We'll note this information. We'll move on to step 5. Step 5, we're going to compare our height computed to our height observed to get an intercept, and we will then plot it using our azimuth up here in our assumed position that we kept from earlier. So the difference between these two values is 4.4 minutes. The computed value is greater than the observed value, so we're 4.4 minutes away. So we're going to go on to the universal plotting sheet. We'll plot our assumed position. We'll plot in a direction of 131.4 towards the GP. We'll also plot away. Then we'll mark off 4.4 minutes from the AP and draw our line of position. So I'm going to speed through that with the magic of movies with the plotting sheet, and I'll get back to you once we've got the preliminary stuff plotted. Okay, so I created the universal plotting sheet, set my center latitude, created my longitude marks, and then plotted my AP. Since the AP is not where we actually were, it's just a mathematical calculation, we can then plot our azimuth. So 131.4, roll it up there, and then we'll plot in both directions, but I'll label this as GP. That's the direction towards the GP. Then our intercept was 4.4, so I'll use the latitude scale to measure 4.4 minutes. Mark it away from the GP, so from the AP away from the GP. At that point, and then our perpendicular line is our line of position of the sun at the specific time of the sight. Remember, this line of position is going to extend thousands of miles out. It's going to create a circle of equal altitude around the GP and kind of come back. So this represents one line of position. We could use it for a running fix, or if you had multiple bodies, you could use it for a fix. Our second example is a moon sight reduction. So we've got our HS, we've got our local time, and our DR position. So let's go through our 5-step process. I will warn you, we're going to go slightly out of order in this one just because it makes sense for the moon. But we need to correct our height of sextant. So our index error said that we needed to apply an index correction of negative 2.6. And our height of eye was 59 feet above the surface of the sea. So that means that our correction here is going to be negative 7.5. So that makes an HA, or a height apparent, of 59 degrees, 48.6. Now the deal with the moon is we need to apply horizontal parallax, don't forget, and that comes from the Nautical Almanac. So in order to do that, we kind of need our GMT, which I usually save for step 2. However, our longitude is 102.39.3 east, so 102.5 divided by 15, because it's roughly 102.5, gives us a time zone of 7 east of Greenwich, so 7 zone descriptor. So that actually puts us back on the 24th of February at 23:22:06 GMT. So with that data, we can get our HP, and then we'll use that again in step 2 of the process. But so February 24th, we can see for the moon in here on February 24th at 2300, we can pull a horizontal parallax of 54.2. All right, so we'll note that 54.2. So then for the apparent altitude for the moon, we go to the back of the book. And remember, there's a dip table that's reproduced here. You don't need to use it, but you can. So our apparent altitude was 59-ish. So that puts us kind of over here in this column. So 59.58 puts us right over here So a 39.1 number one correction. And then stay in that column. In our horizontal parallax 54.2, you can kind of interpolate it. And it said that we used the lower limb. So it looks like our second correction is going to be kind of 2.7-ish, plus 2.7. So these are always added, except 1 degree is or 30 minutes rather, is subtracted for using the upper limb. So in this case, we did use the upper limb, so we're going to subtract the 30.0. And when we do the totality of all that in the calculator, we end up with an HO of 60 degrees, 0.4 minutes. So step one complete, HS to HO with a little diversion for horizontal parallax of the moon. So remember, the big difference with the moon is kind of these extra corrections and using the back of the nautical almanac tables to do the apparent altitude correction. So for step two of the process, we've already done some of the work. We got ourselves to GMT. So we'll just kind of return to the nautical almanac for February the 24th, and we'll pull out some moon values. So for the whole hours of 2300, we can pull declination and GHA and little d number for the moon out of here, and we can kind of note that stuff down. So for declination, the whole hourly values was south 10 degrees, 52.8 minutes, and the little d number was 8.8, and it was increasing, so we have a plus for that one. For the GHA for the whole hours, our GHA was 277 degrees, 10.3. Don't forget, for the GHA, there's a V number as well. So that 14.8 V number. All right. So next, we'll go back into the increments and corrections pages for the 22 minutes and 06 seconds that we haven't accounted for yet. Right there. All right. Declination. So all we need to do really is get the D number. So D number is 8.8. So it looks like our correction is plus 3.3. So we do that out. Our total declination is going to be south 10 degrees, 56.1. So we can note that for later. For our GHA, so we'll look in the moon column here for 22 minutes and 06 seconds. So our first correction is this 516.4, and then for the V number was 5.6. Another correction, our V number was 14.8, my mistake. So a correction of 5.6 there. So we got 5.6 for the V number, which we'll take care of, and we got 5 degrees, 16.4 for the time. So we do that together, we get 282, 32.3. So we got our declination and our GHA for the moon. We are good to go on to step 3. So for step 3 of our process, we're looking for 3 values so that we can go into HO229. The first is latitude. So we're going to choose the closest whole latitude to our DR position, and it's pretty far away in this case, but it's going to be 30 degrees south. So that's latitude. Declination, pretty straightforward, south 10 degrees. And we'll account for those minutes later in the process. But for HO229, we've got the whole value. Now for LHA, since we're in the eastern hemisphere, it's GHA plus longitude to result in a whole number. So GHA is 282, 32.3. 102 for the longitude. And if we choose 27.7 as our assumed longitude, then when we add these two together, we get an LHA of 25. We can subtract 360 from that to get it. So we'll note this as our assumed longitude for our kind of step 5 process. We've got our assumed latitude as well. And now we've got 3 things that we can go into HO225 229 with rather. Latitude, declination, LHA. So when we go into HO 229 with an LHA of 25, a latitude of 30, and a declination of 10, we can pull out our computed value, our D, or altitude difference, and our Z, or azimuth angle values. So we'll note those, and at the same time we'll note the next consecutive Z value is 124, just so we can do that little correction later without having to come into this. So we'll kind of note these values down, and I rearranged the top of the board just for the critical data kind of that we need from there. So our HC, computed height, ended up being 59 degrees, 17.6. Our D, our altitude difference, was plus 41.3, and our Z, or azimuth angle, was 125.4. All right, so now we need to use this D value to correct HC, and we can do the azimuth correction if we want to, depending on the accuracy you're looking for. So D number, 41.3, times the declination increment, all divided by 60, is our correction. So that means our correction is 38.6, and it was an increasing correction there. So our total HC becomes 59 degrees, 56.2. So that's HC. Always good to check against our HO. Yep, they're pretty close, so we're probably on the right track. For the Z value, if we want to correct this, we can note the next tabular Z was 124. So there's a difference of 1.4 there, minus 1.4 degrees for the sequential ones. So if we take this, multiply it by the declination increment, divide it by 60, that ends up being our correction of negative 1.3. So 125.4 minus 1.3 is 124.1. So that's our Z. Then we need to apply the azimuth rules. So we're in the southern hemisphere. So if LHA in our case was 25, so it's less than 180, 180 plus Z is our azimuth. So 180 plus our azimuth angle is our azimuth, and that's going to be 304.1 degrees true. So we've got our ZN, we've got our HC, onwards to step 5. So for step number 5, we've got our height observed from step number 1, our height computed from step number 5, and the difference is going to be 4.2 minutes. Since the height observed is more, we're towards. So we're going to plot towards the GP. Our ZN is 304.1. So in essence, we'll set up our universal plotting sheet. We'll plot our AP. We'll plot towards the GP of 304.1 and a little bit away always just in case. Then we'll take 4.2 towards the GP, make our mark, and that's going to be our LOP. Our next site reduction is of a planet, Venus. So step number 1, we'll take our HS and convert it to an HO. So in the problem, it stated that we have an index error, so an index correction of plus 4.5. And our height of I was 55 feet. So we can pull out our correction of negative 7.2. That gets us to an HA, a height apparent, of 12 degrees 50.7. Now this is not a low altitude site, but it's pretty low, so just always be aware of that. So the other things we got to do is look for Venus corrections. So we're going to do our star and planet correction and additional Venus correction if necessary. So for the apparent altitude, it looks like our correction is going to be negative 4.2, And our Venus correction for the season that we're in May, is going to be a plus 0.1. So minus 4.2 plus 0.1 gets us our HO, height observed, 12 degrees, 46.6. All right, so step 1 complete, HS to HO. For step 2, we've got to get the geographic position of Venus at the time of sight. So we're already given our GMT. So this was 25 May. So for the 25th of May, we can look in the Venus section here. And at 08 GMT, we can pull some of our data out here for the declination and the GHA of the planet. So we'll also pull our V numbers and D numbers as well. So for the declination, our hourly declination is north 23 degrees, 12.8. It's increasing and the D number is 0.4. For our GHA hourly, our GHA was 287, 25.7, and our V number was negative 0.9. So next we'll go into the increments and corrections pages for 5750 to account for that. We'll look in the sun and planets column. So for 57 minutes and 50 seconds, we'll pull out 1427.5, and then we'll look at our V number. And our V correction, based on our V number of 0.9, is going to be also 0.9, which makes sense. We were almost at the end of the hour here. So for declination, it was increasing, and our declination based on the D number, 0.4, is also 0.4. So our total declination is north 23 degrees, 13.2. So that's good to note. Our GHA, kind of keep track of all those corrections that we made, 14 degrees, 27.5. And the V correction was negative 0.9. That means our total GHA is 301 degrees, 52.3. All right, step 2 complete. Onwards to step 3, we need to get our factors to go into HO 229. So declination is easy. That one's going to be 23 degrees north. Latitude is 21 degrees north. So we're on the same pages in this case. In our LHA, since we're in the eastern hemisphere, GHA plus longitude. So 301, 52.3 plus something that results in a whole value of LHA. So what the whole value will be. So we got to do a little bit of work in this case. We're going to choose 143 degrees, 07.7. So that's our assumed longitude. We'll note that for later for the AP. And that gets us our LHA of 85 degrees if we subtract 360 from it. So we've got our 3 factors, declination, latitude, LHA. Onwards to step 4. All right, for step 4, we get our LHA of 85 on the same pages. Latitude 21, declination here. Declination 23. So we're going to pull out values of HC, D, and Z. We'll also note the next sequential Z, just for our correction process if we choose to do it, 68.9. You can note all that down. So our computed height was 12 degrees, 24.7. D value was plus 18.2. Z, azimuth angle, was 69.9. And the next sequential one was 68.9, just in case we choose to do that. You don't always have to do the Z corrections, but in case you want to. So we'll multiply our D number, 18.2, times our declination increment, all divided by 60, to get a correction of 4.0 plus. So our HC is going to be 12 degrees 28.7 is our final HC value. So we'll note that for step 5. For Z, we can note the difference between the sequential Z's if we want to, and multiply that by the declination increment. So 1 times 13.2 divided by 60 gives us a correction of negative 0.2. So you can almost always ignore this, but if we do that, we get 69.7 for the Z, and then using the azimuth rules, since the LHA is less than 180, Zn is 360 minus 69.7, or 290.3 for our Zn. All right, so up to you if you do this Z interpolation or not. You can safely skip it for sure, but we're just showing it here for completeness. So we've got our HC and our Zn onwards to step 5. So for step 5, we're going to compare our computed height to our observed height and note the difference. So the difference between these two, we can get rid of this declination, I guess. The difference between these two is going to be 17.9. And the observed value was more, so we're towards a Zn of 290.3. So for our plotting sheet, we'll plot our assumed position of 21 degrees north, 143.07.7 east, and then we'll plot in a direction of 290 and also away from it. Note that it's the GP, and then march off 17.9 towards the GP and draw our LOP that way. We're going to omit the plotting sheet in this case because, quite frankly, I'm all out of them, but I think you get the picture at this point of how to plot these. For this example, we've shot in a star, so the star Antares. We observed a sextant height of 3222.5 at this time and at this DR location. So step 1, we need to convert this to our HO. So our index error, as given in the problem, says that we need to apply an index correction of plus 2.0, and our height of eye was 10 feet. So in our dip tables, we can look at a height of eye of 10 feet to pull out a correction of negative 3.1. That gets us to an apparent altitude of 32 degrees, 21.4. From there, we need to apply our apparent altitude correction. So since we're doing stars, there's no planet correction, there's no additional correction, there's no abnormal conditions correction. So we've just got a simple one right here, and we can look that up and get a correction of negative 1.5. So that means our HO, our height observed, is 3219.9. So we'll save that for later in the process. For step 2 of the process, we need to first correct our time to Greenwich Mean Time. So our longitude is 4630 west, so that means that our zone descriptor is 3 hours to the west of Greenwich. So that makes our GMT 23:15:04. So that's what we'll look up in the Nautical Almanac. And it's the 4th of September. So for Antares, the declination and the SHA are noted here. So I'm going to note those down first. So the SHA for Antares rather is that's kind of a standard value. So then for the 4th of September at the appropriate time, we'll pull out the value for the GHA of Aries. So that's 328 degrees, 58.2. So you can do these kind of in any order, but for first thing I'm going to do is I'm going to apply the increments and corrections for the 15 minutes and 4 seconds. So for Aries, 15 minutes and 4 seconds, 346.6. And then this goes here as well. So we total that up. We get the hourly GHA, the increments of GHA and the SHA, that gets us a total GHA. If we subtract 360 degrees of 85 degrees, 40.9. You can always subtract 360 if you get too high there. So we've got our declination, we've got our GHA, step 2 complete. Moving on to step 3. So for step 3 of our process, we've already got a declination, our height observed, a GHA. We need to pick 3 things so that we can go into HO 229. We need a latitude, and that's going to be very easy. We can just use the nearest whole latitude from our DR position. So that's going to be 17 degrees north. Our declination, we've already got, it's going to be south 26 degrees, and that means we are contrary, and we'll have to account for these leftover increments later in the process. For the LHA, since we're in the Western Hemisphere, this is going to be GHA minus longitude. So our DR longitude was 46 degrees, 30.5 minutes west. So if we want this to come out to be 0, so if we make this 40.9, then that makes our LHA 85 minus 46, or 39 degrees. So this becomes our assumed longitude. So LHA of 39 degrees. That wraps up step 3. We can move on to step 4. So for step 4 of the process, we'll be on the contrary page, our LHA 39, latitude 17, declination 26. And so we can pull out some values here. And that's going to be 3240.2 for the HC, negative 42.1, and then 137.8 for the Z. We'll also pull out the next sequential Z, 138.6, so that if we choose to do that interpolation for the azimuth, we can. You don't have to do that. We'll do it in this video just for completion, but that makes our HC 32 degrees, 40.2. Our D number, our altitude difference, was negative 42.1, and then our Z was 137.8, and the next Z was 138.6. So let's just deal with that now. That means there's a difference of 0.8 in there, and it's an increase. So like I say, you don't have to do this altitude or this azimuth interpolation if you want, but if we take the 0.8 times the 23.3 leftover declination increment and divide it all by 60, you get a correction of plus 0.3 to apply to your original one. So that makes this 138.1 for Z. All right, and then since the LHA is less than 180, depending on our hemisphere, that makes our azimuth, our ZN, is going to be 221.9 degrees true. All right, so for the declination, or sorry, for the altitude difference, we're going to multiply this by our 23.3, divide all that by 60, and that gets us a correction of negative 16.5 and a total HC of 32 degrees and 23.7. All right, so that's it for step 4. For step 5, we'll compare our computed and our observed altitude. So let's get rid of all this, the rest of this stuff. And the difference there, the difference between these two ends up being 3.8 minutes. And since the computed is greater, we're away. We already got our azimuth. It was 221.9 degrees true. We corrected the azimuth and then applied the azimuth rules. So if we go to the plotting sheet and plot this, we're going to plot our assumed position of 17 north, 4640.9 west. We'll plot 221 towards the GP and then also plot away from it. And then we'll march off 3.8 away and draw our LOP, and that's going to be the solution to this one. Well, we've reached the end of this course. I hope you've had a good time learning the 5-step celestial sight reduction process and getting some practice problems in along the way. This has been a great voyage. Where do you want to go next? Well, it's kind of up to you. I would say that if you are a recreational mariner and you want to do this stuff forever, just practice your sights every time you're underway. Whenever you get a chance to break out the sextant, go for it, especially the noon sight for latitude. If you have more time, work on the sight reduction process. If you're a professional mariner looking to advance your career, whatever jurisdiction you're in, there's going to be some governing body that licenses you for oceans navigation or celestial navigation. Be sure to check out those sample exams, work through the problems. There might be some nuances to the steps that we've done in this course. For example, in the US, there's this is the basic sight reduction process, and from here you can go learn to do all the other stuff that's required on a Coast Guard exam. Practical Navigator Training, the company that I operate, we have some celestial navigation resources available for US Coast Guard licenses, so be sure to check those out if you like. And then otherwise, go out there, practice this, and happy navigating.